sklearnexceptionsundefinedMetricWarning. Description: this warning is issued by scikit-learn sklearn when a metric is calculated for a dataset where the metric is undefined or not meaningful. This typically happens in situations where the target labels have only one unique value. For example, if all samples in your dataset belong to the same class, calculating metrics like accuracy or F1 score becomes meaningless. The predicted values are all the same if your model consistently predicts the same class for all samples, regardless of the true labels. Metrics like precision, recall, and F1 score will not be informative. Inputs: data, the dataset used for training and evaluation, consisting of features and target labels. Model, the machine learning model used to make predictions. Outputs: predictions, the model's predicted class labels for the dataset. Metrics, the calculated performance metrics, which might be undefined or not a number due to the warning. Steps: data preprocessing, prepare the dataset, including handling missing values and feature scaling. Model selection, choose an appropriate machine learning model based on the problem and data. Characteristics: training, train the model using the training data. Prediction, apply the trained model to make predictions on the test data. Metric calculation, compute performance metrics using the predicted and true labels. Metrics: accuracy, the proportion of correctly classified samples. Precision, the proportion of correctly predicted positive samples out of all predicted positive samples. Recall, the proportion of correctly predicted positive samples out of all actual positive samples. F1 score, the harmonic mean of precision and recall. Visualization plots. Confusion matrix, a visual representation of the predicted and true labels, showing the number of correct and incorrect predictions for each class. ROC curve, a plot showing the true positive rate against the false positive rate for different classification thresholds, used to assess the model's ability to discriminate between classes. Fine-tune parameters. Model hyperparameters adjust the model's internal settings, such as the number of hidden units in a neural network or the regularization strength in a linear model. Data augmentation, generate additional data samples by modifying existing ones to improve the model's robustness and generalization ability. Uncertainty methods. Confidence intervals, calculate confidence intervals for the performance metrics to estimate the range of possible values. Bootstrap resampling, repeatedly draw samples with replacement from the dataset to assess the variability of the metrics. Challenges and fixes. Challenge 1, data imbalance. Sample use case that resulted in challenge 1 in a dataset where one class significantly outnumbers the other. The model might always predict the majority class, resulting in high accuracy but poor performance on the minority class. Fixes to challenge 1. Oversampling, duplicate samples from the minority class to balance the class distribution. Undersampling, remove samples from the majority class to reduce the imbalance. Class weighing, assign higher weights to samples from the minority class during training. Challenge 2, model misspecification. Sample use case that resulted in challenge 2, choosing a model that is not suitable for the data, or the task can lead to inaccurate predictions, especially if the data contains complex relationships. Fixes to challenge 2. Try different models, explore a variety of models, including linear, nonlinear, and ensemble methods, to find the best fit for the data. Feature engineering, create new features or transform existing ones to improve the model's ability to capture the underlying patterns in the data. Regularization, penalize model complexity during training to prevent overfitting and improve generalization. Challenge 3, data noise. Sample use case that resulted in challenge 3 noise or errors in the data can lead to unpredictable behavior and inaccurate predictions. Fixes to challenge 3. Data cleaning: identify and remove outliers or incorrect entries from the data. Robust methods use robust estimation techniques that are less sensitive to noise and outliers. Feature selection: select the most relevant features that contribute to the target variable, reducing the impact of noisy features.